Welcome back. We are looking at temperature and solvent effects. And in today's lecture, we're going to be looking at polymer solutions, where we are going to be looking at solvent effects largely. And this theme will continue in the next couple of lectures as well. So, in today's lecture, we're going to be focusing on what it means to dissolve a polymer. We've looked at the solid state of polymers earlier, where we've specifically looked at the microstructure both for semicrystalline and amorphous polymers. Now we are asking, if you take that polymer and you try to prepare a solution, you dissolve it, what does that process look like? So we're going to look at stages of dissolution, the different steps involved. As we will see later in this lecture, the steps involved for dissolution of a polymer are quite different from dissolving a small molecule such as a salt. We will also look at solubility parameters that can help you give some idea about polymer-solvent interactions. And in that same vein, we will also look at solvent quality. You have a good solvent, what does the polymer do inside in the solution versus a poor solvent, for example. And then we will revisit this idea of real change and excluded volume that we have earlier looked at briefly. We will revisit that theme and try to understand it better from the perspective of polymer solutions. And we will also look at chain overlap and entanglement. We will ask this question of what happens if you keep adding more and more polymer into a solution. And we will finally end with, as always, bulk manifestations. And that's always the theme that we are interested in, which is to ask, how do these properties ultimately affect bulk macroscopic behavior, which you can visualize. So we'll first ask this very simple question: what is so special about the effects of solvents on polymers? And for that, the starting point is something that would be more familiar to us, where we will consider the example of a small molecule, such as a salt. So now if you consider the dissolution of a small molecule, if you take salt, you try to dissolve it, crystals, and you try to dissolve it in water, you will see that the solute-solvent interactions are established almost instantaneously. So in the case of salt, the solute molecules ionize and leave the crystal lattice, and as they leave, these ions rapidly diffuse into the solvent. And ultimately, once all of the salt is dissolved, you get a homogeneous solution, where the salt and the water are molecularly mixed very well to form a homogeneous solution. And there are two interesting aspects about this process. You will see that if you stir it with a spoon, or if you heat it, for example, this process will go faster. And if you keep adding more and more salt, at some point you will realize that that solution can no longer take any more salt. So any more salt that you add in will not be soluble because that solution has reached supersaturation. So this is a very familiar example of this simple dissolution of a small molecule like salt or sugar in water. Now, what does the situation look like for polymers? In polymers, right away, you see that the big difference for polymers from small molecules is polymer molecules take up appreciable volume. Now, this is something that we have seen earlier when we have looked at number average degree of polymerization, when we have looked at molar mass, etc. This is a very important idea in polymers, and that makes a very big difference to how polymers go into solution. You have chains, which would be random coils, and you can have entanglements. And they are not discrete, unlike the ions that we saw in the salt case that can come out and diffuse right away. What's also important is, because these chains are long and the chains can interact, you have a large number of secondary interactions across chains, as we had seen earlier, and that plays a very important role in how quickly or how slowly a polymer will dissolve. So these could be dispersion, for example, dipole-dipole interactions, or even hydrogen bonds. It could be a bunch of different non-covalent secondary interactions that hold the chains together. As a result of these secondary interactions, um, the coiled nature of the macromolecule and the very large size, the high molar mass, dissolution is a slow and multi-stage process. So, three things contribute to that largely. One is the very large size of the macromolecule, the molar mass, the secondary interactions that exist across these chains, and the coiled nature of these chains. All of these contribute towards making polymer dissolution a much slower process compared to the dissolution of a small molecule. And the conformations, once it is dissolved, the conformations in solution will depend on solvent quality, which we will look at in much more detail later in this lecture. And unlike the salt case, where you keep adding more and more salt, you don't see any appreciable changes in viscosity. Whereas when you keep adding more and more polymer to a given solvent, you will start to see properties changing macroscopically. One manifestation of that is viscosity. So, these are some key differences to note as we delve further into understanding the process of polymer dissolution itself. So, let us as always consider a physical picture of polymer dissolution. Some key aspects involve solvent diffusion, disruption of interchain secondary bonds, you have segmental mobility that increases as the solvent penetrates, you have swelling of the polymer, and you have chain disentanglement. You see, there are some aspects that are similar to what would be for a small molecule, but many of them are very different. And the key words to note here are, there is diffusion of solvent, there is swelling, and there is chain disentanglement. These are three very important characteristics that are important for understanding the dissolution of a polymer in a solvent. And shown here is just a schematic representation of this process, where the polymer is an entangled mass like this in the solid state. Again, shown here is only a representative cartoon. Once you add the solvent penetrates or diffuses into the polymer and plasticizes it. We are talking about a glassy polymer, it's going to plasticize it. And it forms what we call a swollen gel. The polymer entire system increases in volume because of swelling, and it forms a gel-like structure. And eventually you will end up with these chains that are completely solvated. And the fact that we have drawn red dots or these circles enclosing these chains should indicate to you that we are trying to represent it as a blob or a sphere. And what might immediately come to your mind when we think about this kind of a picture is a concept we have seen earlier, which is hydrodynamic radius, or in this case hydrodynamic volume. This should come to your mind when you look at a picture like this. Of course, the chains are also spaced apart, and later on we will see in this lecture that is also a function of polymer volume fraction. How much polymer is eventually present, or the polymer to solvent ratio will determine whether chains are still entangled, or chains are overlapping, or chains are very far apart. These things are all determined by how much solvent you have added and what is the polymer volume fraction in the final solution. So, that is the first understanding that we have of polymer dissolution. Now, we will look at this process in some more detail. And like I said, there are four key aspects that you have to consider when you think about polymers: diffusion of solvent, swelling of the polymer, unfolding of chains, and solvation of chains. How does this happen? This is something we are going to look at systematically. So, when you take a polymer and you add a solvent to it, and here we note that the polymer we are talking about could be an amorphous or a semi-crystalline polymer, and there are some subtle differences there that we will look at in the next slide. But largely, we're looking at linear or branched, uncross-linked polymers. Because if you have cross-linking, you will have other kinds of effects that we will look at later. When we look at hydrogel swelling, for example, hydrogel is a cross-link network that swells in water. And there, you're going to have swelling of the network itself that happens. That is not the same as the swelling I'm talking about here. There, the cross links between the chains have a close interplay between the solvent penetration into the network. So, we are not considering those kinds of systems here. We are considering uncross-linked, linear or branched, amorphous or semi-crystalline polymers in this lecture. So, when you add solvent, what happens is solvent starts to diffuse through the matrix, and as it starts diffusing, the solvent disrupts chain-chain interaction. These are secondary bonds that exist between the chains, and those interactions are disrupted. Now, we are making an assumption here that this is a good solvent. In other words, the polymer-solvent interactions are favored over polymer-polymer interactions. And that is one of the scenarios in which these secondary bonds can be broken up because solvent now penetrates and the polymer wants to interact with the solvent more than it wants to interact with itself. And as a result, what you have is matrix swelling and volume increase. So, you have this mass through which solvent is getting inside, and as solvent gets inside, it increases the space between the chains and swells the matrix. So, that's the second step of swelling. The solvent is diffused. Now, the mass, the polymer starts to swell, and that leads to an increase in the volume of the system. And because solvent can now free up those interactions, you now start to get segmental flexibility, and you have relaxation of chains. Now, you have to connect the segmental flexibility to some of the concepts that we have seen earlier when we were discussing glass transition and amorphous polymers. Eventually, there is disentanglement and dispersion, and what happens as a result of that is the solvated molecules, where now each polymer chain is surrounded largely by solvent, diffuses out of that swollen mass. You have the swollen mass where solvent has gotten inside, and eventually, with enough solvent penetration with time, because of disentanglement, dispersion occurs, which means the solvated macromolecules diffuse out of the swollen mass. And eventually, what will end up getting, and this happens for all chains, what will end up getting is a molecularly well mixed homogeneous solution. Now, this should give you a sense of why this takes time, because there is a time scale associated with diffusion, there is a time scale associated with swelling, there is a time scale associated with unfolding of chains, where now the chains start to interact with the solvent more than it wants to interact with itself, and it gets fully solvated. So, there are specific time scales associated with each of these, and as a result of which, the entire process takes far more time than for a small molecule. And ultimately, what you will end up with is what we call a solvated shell, as shown in this cartoon here. And you can think of, eventually, once the solution is formed, is homogeneously formed, a well mixed solution, you can think of an equilibrium that has been established from a thermodynamic perspective between the solvent that is quote unquote bound to the chains or in the vicinity of the chain, and the free solvent that is away from the chains. There is an equilibrium that is established between the movement of solvent molecules between the free state and the bound state. One important idea to keep in mind is, while the chains may retain their coiled nature, in a good solvent, you will have the chains expanding. And remember, we have seen this when we looked at conformations in lecture 9, where we have seen that in a good solvent, you will have a size that is higher than what is predicted for an ideal chain. And that's because you have an expanded chain. So, that is important to keep in mind. So, the coil-like structure may get retained, especially at dilute solutions, but the chains are now in the expanded state. So, we now consider the case of both amorphous and crystalline polymers. When I say crystalline, I am talking about the crystalline domains of a semi-crystalline polymer. Remember that no polymer is truly 100% crystalline. When we say crystalline polymers, it should be understood that we are talking about the crystalline regions or domains within a semi-crystalline polymer. So, you now consider an amorphous glassy polymer, and typically these polymers are operated below the TG. Because if you remember earlier when we talked about amorphous phase and glass transition, we talked about the use temperature or operating temperature vis-a-vis the TG. So, many of these glassy polymers will be operated below their TG. Of course, for rubbers, they are anyway above their TG, and anyway the free volume is higher. So, solvent can easily penetrate, but we are considering the case of a glassy polymer here, typically operated below its TG. So, if you think of what happens to such a system when you put it in contact with a solvent with which it can interact, the solvent is going to slowly move into the glassy polymer. The polymer gets plasticized, and by plasticized what we mean is a lowering of TG, increase in free volume followed by rapid swelling. And then that boundary between swollen and unswollen layers keeps moving, and ultimately once all the chains are fully solvated, then you have a full solution, at which point the polymer chains have diffused out of the swollen mass into the solvent. Now, if you consider different regions of this process, if you take a snapshot and you consider that there is bulk solvent on one side and there is the glassy polymer on the other side, very close to the bulk solvent you have a liquid like region or almost a liquid region with very high segmental mobility. These are what you would call fully solvated. And then as you go here and here, in this region you have what you would call a swollen gel, where there could still be entanglements, but the solvent has penetrated enough such that the spaces between the chains have opened up, the secondary bonds have been broken, and what you have is a swollen gel-like structure. And you go further inside, you go to the infiltrated layer, where solvent has indeed penetrated, but the chain-chain interactions are still dominant there. And eventually it will become swollen with more solvent penetration. To the final region where you have only glassy polymer which we are trying to dissolve. So, many a time you will see that when you want to dissolve a polymer, if you have a film for example, typically it is very common to cut it into pieces and put it into a solvent. I would encourage you to try and think of why that is helpful. Based on our understanding of how polymer dissolution happens from this kind of a picture, can you now speculate and imagine why it might be helpful to cut up a film of polymer into smaller pieces and put it into solvent to aid dissolution? It's something that I would encourage you to think about. Now, this is the case of an amorphous polymer, but as you will see, for a crystalline polymer or the crystalline domains within a semi-crystalline polymer, the situation is slightly different. Remember, when we are talking about crystalline polymers, immediately what should come to your mind is this ordered lamellae-like structure, and that's going to hinder diffusion because the secondary bonds holding the lamellae are much stronger compared to the amorphous tie molecules. In the amorphous region, there is no really order. So, solvent penetration is not going to be that hard. In fact, when we look at degradation later, we will see that when you have a semi-crystalline polymer in an aqueous environment, and you're looking at hydrolytic degradation, water penetration, which is analogous to solvent dissolution, um, will first occur in the amorphous regions. Those are easily more attacked compared to the crystalline regions, which get attacked much later. And the reasons are not hard for us to see because of the ordered structure and the significant secondary bonds that hold them together. So, very specialized solvents are typically needed for disrupting the bonds between the lamellae. And not only that, because we are looking at temperature and solvent effects, oftentimes you will see that a solvent alone will not make the cut. You might, in many cases, need heat to also be supplied for the polymer to dissolve. Essentially, you are letting the crystallites melt or aiding crystallite melting. As an example, polyethylene will be much more soluble in toluene when it is heated. And if you consider polystyrene, and if you're wondering, what if I have isotactic and atactic polystyrene? Atactic polystyrene may be soluble in a solvent at ambient temperature, but isotactic polystyrene will typically be soluble only at higher temperatures. It might not be very hard for you to see why that is the case. You have to associate isotacticity with more order, higher degree of secondary bonds, which means it's going to make it harder for a solvent to penetrate and break those bonds, as compared to largely amorphous atactic polystyrene, where there is no long range order, so the solvent can easily penetrate. So, you see how we are trying to connect a concept that we have learned earlier as part of polymer configuration. We looked at tacticity to the ability of solvent to penetrate and disrupt the bonds and dissolve the polymer. Having now understood what it takes for a polymer to dissolve based on its microstructure, we will now delve deeper into understanding solubility of polymers from a thermodynamic perspective. Now, we will do a more rigorous version of this in a later lecture, and we look at the Fleury-Huggins theory. But here in this lecture, our goal is to understand the contributions from a thermodynamic perspective to the free energy of mixing, and then trying to come up with parameters that can be used to classify solvents as good, poor, etc. So, firstly, we note that at constant temperature and pressure, any system will tend towards minimizing Gibbs free energy. So, this is something that we are familiar with from many of the courses that we might have taken. In this very famous equation, where delta G is given by delta H minus d delta S, and typically people talk about spontaneous or non-spontaneous depending on direction of change for delta G. More correct way to think about it is thermodynamically favorable versus not. So, negative delta G, which tends towards minimizing free energy, is typically favorable for dissolution. That's a very good starting point for us. Now, we can ask, what are the contributions towards delta G? Broadly, if you think of entropic and enthalpic contributions, the delta S change for mixing when you add a solvent will be favorable because the number of available microstates increases in solution. This is true for mixing of two liquids, where the number of different conformations that the system can now be in increases in the mixed state as opposed to the individual state. So, delta S is going to be favoring dissolution or mixing, where you have high segmental and molecular mobility leading to a larger number of conformations that the system can take, which we call microstates. Now, delta S being positive, that obviously is going to favor mixing because that's going to lead to a lowering of the energy. So, if you really think about it, it's the enthalpic change delta H which is going to eventually determine if solubilization is favorable or not at a given temperature. Now, this is very, very important, and this is why we are looking at both solvent and temperature effects together. All of this is meaningful only when you specify the temperature. As we saw in an earlier slide in this lecture, sometimes heat is required to solubilize some polymers, even in the presence of a solvent. And so temperature effects are very important, and you can't really decouple many of them. So it makes sense to talk about many of these effects together. So that's the question now. How do we determine the delta H? One way to think about it is coming to us from Hildebrand and Scott theory for mixing of two liquids. Here, this is applicable only for a positive delta H. The M here simply means mixing. The basic idea here is like will dissolve like. So, if you have two different liquids, solvents for example, if you want to mix them, if they are alike in terms of some property that we will look at, then mixing is favored. That's the basic premise behind Hildebrand. Now, when you talk about two different solvents coming together, obviously they're going to interact. And the type of interactions that Hildebrand accounts for is only non-polar van der Waals interactions. It does not account for polar interactions or hydrogen bonding, which we will see very often with many systems. But the Hildebrand theory does not account for that. And it gives an expression for the change in enthalpy during mixing as given by this expression. Now here, Vm or V sub n is the volume of the mixture. Delta E, whether it's 1 or 2, both of them, is the energy of vaporization at 0 pressure. We will look at what that is in just a second. V sub 1 and V sub 2 are the molar volumes of the two liquids, and Phi1 and Phi2 are the volume fractions of the two liquids. Now, this delta E over V is called the cohesive energy density. Essentially, it is the, you can think of it as the energy holding the molecules together in the liquid state, and the energy required for them to break apart from the liquid state and vaporize. So, that is why it is called the energy of vaporization at 0 pressure, where it is the energy required or the energy holding the molecules together in the liquid state and the energy required for you to release those molecules from the liquid state to vapor state. Another way to think about it is in the gaseous state, you can think of the interactions at infinite separation, where the molecules are all very spaced apart very far. And the Hildebrand theory defines something called a solubility parameter based on the cohesive energy density, and simply it is square root of the cohesive energy density. And the idea here is, if you take two liquids, you can now define delta 1 and delta 2. So, this happens to be delta 1, this happens to be delta 2. Now, remember that closer they are, that is closer delta 1 and delta 2 are, which is the property that Hildebrand largely relies upon, more favorable is mixing. That is what we meant by saying like dissolves like. Now, how do we contextualize this for polymers? Before we do that, one point to note here, and this simply comes from inspecting the equation, is you notice that this theory will always predict positive values for delta H because of this term. And that is why we said it's applicable only for positive delta H. This comes simply by inspecting the equation, and that's a very important skill that you can learn by just inspecting equations. You can learn a lot about the physics of or the limitations or the advantages of different equations. Is delta H always positive? Not really. But is the Hildebrand still useful? Yes. As it turns out, For many polymer systems, polymer solvent systems, instead of taking two liquids, if you take a polymer and a solvent, for many of them, delta H is positive, which means Hildebrand is widely applicable. So, if you consider the case of a polymer, you have polymer solvent interactions, and as we saw, delta Hm is proportional to this delta 1 minus delta 2 the whole square, where 1 refers to solvent, 2 refers to polymer. And as we have seen, this term, that is the difference between the solubility parameters, eventually determines the solubility. And we have seen that it's always going to be positive based on the Hildebrand prediction. So, Hildebrand will not really apply for polymers that interact strongly with solvents where the heat of mixing will be negative. The theory will not hold there. So, in such cases, dissolution is still going to occur even if this term is appreciable. And that's because of thermodynamic considerations, because heat of mixing is anyway negative. But those are more rare. For many polymer solvent systems, you will end up actually getting a positive heat of mixing. So, Hildebrand is actually widely used. And just to point out here that the theory that we have looked at is more general. If you can think of two solvents, one point to keep in mind is, if you remember our earlier discussion in this lecture, the solvent molecules will have similar sizes. Now compare that with the case we have here, where polymer solvent molecules will not have the same size. That will have a lot of repercussions for the thermodynamics of mixing, which we will see again when we do Fleury-Huggins in more detail. But for now, perhaps keep that in the back of your head, and we will revisit that idea later when we do Fleury-Huggins. So, shown here are some numbers for the solubility parameters, and you see immediately from the units why it is called the cohesive energy density. It's reported in cal per centimeter cube, the whole to the half, and you will also have more commonly the megapascal to the half also being used, and from simple dimensional analysis you can show that these are equivalent, and I will leave it as an exercise to you. But what's important to keep in mind is when you're looking at the parameters, it's important to ask what units are you working with, and if you have one, you can get the other as well. Now shown here are the solubility parameter, the Hildebrand parameters for 3 solvents and 3 polymers. And just based on the Hildebrand theory that we have looked at, if it's the difference between the solubility parameter for polymer versus solvent that's going to determine the solubility or for it to go into solution, then you can do different combinations of these, find differences and see what the magnitude is. That might help explain why polymethyl methacrylate dissolves in acetone, where you see the values are quite close. The closer they are, the more propensity for them to dissolve, because the idea is like dissolves like. As opposed to methanol, where PMMA will not dissolve easily. But you notice, if you look at PEO and water, they are very far apart in terms of the solubility parameter, and yet PEO will very easily dissolve in water. Can you try and speculate why Hildebrand doesn't predict solubility for this kind of a system? If you have guessed right, you would have guessed that these interactions between water and polyethylene oxide are not limited by van der Waals or non-polar interactions, but they are largely governed by hydrogen bonding, and those interactions are not accounted for. So, other kinds of interactions such as polar or hydrogen bonding are not accounted for by Hildebrand, and that's why simply looking at the Hildebrand parameters will not help us predict that PEO is soluble in water. because those interactions are not accounted for. But nevertheless, for many organic solvents and polymers, Hildebrand works quite well. And if you look at the literature, you will see ranges. If the difference is less than a certain value, then they will say it's soluble. If it's slightly higher than that, they will say it's partially soluble. And if it's above a certain value, they will say it's insoluble. So you can look at some examples in the literature, and I've shown you some examples here. You can also look at other examples in the literature and see what those limits are and how to understand them. But again, remember, these are rules of thumb. Now, one other theory that you will often hear is this theory by Hansen. In fact, you will find Hansen parameter handbooks, where idea is not very different from Hildebrand, but now Hansen accounts for polar dispersion and hydrogen bonds. So, Hansen is another theory that accounts for all three interactions between the either polymer and solvent, or two liquids, or even drug and polymer. So, largely comes to us from this idea called group contribution theory, where the properties of the individual functional groups are thought to sum up together and contribute to the overall property of the molecule. And if you start at that point, Hansen then showed that you can come up with equivalent Hansen parameters like you had for Hildebrand parameters. You can come up with Hansen parameters that not only account for van der Waals dispersion kind of interactions, but it also accounts for polar and hydrogen bond. So, it does a better job of predicting solubility. And there again, you can ask what is the difference in Hansen. You can think of it as a sphere or Hansen space. And you can ask what is the difference between the Hansen parameters, and you can find out if it is very close. If the parameters are very close, then you will see that it predicts miscibility or solubility. And if it's above a certain number, then it will predict immiscibility. In fact, like I said, you can also use it to predict drug polymer miscibility in the solid state, where if you're looking at loading drugs, we're looking at a polymeric biomaterials course. So, one very important application of polymeric biomaterials is in controlled release. And if you're looking at drug release, you're going to load drugs into polymers and process them. You're looking largely at drug polymer miscibility in the solid state. So, there also Hansen can be used to predict. So, now may be a good time to pause and look up Hansen and compare and contrast it with Hildebrand. One subtle point to keep in mind as we move on is for the Hildebrand solubility parameter for small molecules, we said, or liquids, for example, we said it depends on the cohesive energy density, which is simply the energy required for molecules to go from the liquid phase to the vapor phase, right? For a polymer now, how would you determine this? Because for a polymer, if you take a viscous melt and heat it, you will end up with, if you keep heating it further and further, you're going to end up with polymer decomposition. You will never end up with polymer vapor. That's not a very meaningful thing to talk about. So, then how is the cohesive energy density determined at all? That's a very interesting question you can ask. So, these are some important aspects to think about, and you can gain more insights into these aspects when you ask questions such as how do I physically understand the cohesive energy density? How do I physically understand the solubility parameter, and how is it even experimentally determined? When you ask that question, you will immediately realize that the situation is not as simple as it is for a liquid or a small molecule. It's going to be more complex than that. So, such questions are important for you to ask to get a very good physical understanding of some of these parameters. Otherwise, they will simply remain some parameter in some textbook. For you to really understand what is going on, try to visualize it physically and ask questions such as these. So, having looked at polymer dissolution and having looked at the solubility parameter for polymer solvent interactions, we will now move on to a familiar concept that we have looked at, which is polymers and solvent quality. Now, imagine the polymer has been dissolved, and the dissolution itself is dependent on polymer solvent interactions, as we have seen. And the chain conformation in solution is going to be affected by the solvent quality. And the nature of the polymer solvent, more importantly temperature as always, is going to affect the solvent quality. So, we see here that not only do you have to account for intrinsic polymer solvent interactions, but you also have to keep track of temperature, as that can also affect the solvent quality, as we will see very shortly. You can now use our understanding of polymer solvent interactions to largely classify solvents into three types. This is a simplified picture for this course for our understanding, where you can talk about a good solvent, you can talk about a poor solvent, you can talk about a theta solvent. Now, a good solvent is that such a solvent wherein interactions between the polymer and the solvent are favored. So, the polymer wants to interact with the solvent more than it wants to interact with itself. And in such a solvent, the polymer coils will expand to maximize the solvent interactions, leading to an expanded chain. As opposed to a poor solvent where the polymer-polymer interactions are preferred more than the polymer-solvent interaction. So, when you start adding solvent, the polymer chains want to sort of cuddle up together, if you want to think about it that way, rather than extending themselves and interacting with the solvent. So, they want to minimize their interactions with the solvent. In fact, any solvent that tries to get in will be expelled quite quickly. And that results in the polymer coils collapsing, resulting in a collapse chain. Now, somewhere in between, you have something called a theta solvent, where the solvent is poor, but it is just poor enough that it exactly cancels out excluded volume effects. Excluded volume is simply the idea that no two polymer segments can occupy the same region in three-dimensional space, right? So, this segment here or this region here will say, okay, this is my space. So, another region cannot come in the vicinity. So, that leads to the idea of excluded volume in polymer, which is unique to polymers. Now, in a theta solvent, this poorness of the solvent is just poor enough that it wants to collapse, but not so much that it goes to a collapse chain completely, but it collapses just enough so as to exactly cancel out the excluded volume effects. Essentially, mixing enthalpy is 0, leading to ideal chain behavior, or net excluded volume effects are 0. Now, you can quantify solvent quality different ways. One way to do this is to look at something called an expansion factor alpha, which is mean square end-to-end distance in that solvent to that in the theta solvent. So, this 0 simply indicates that it is the ideal or the theta solvent here. Sometimes you will see that subscript in textbooks referring, and you should remember that that is the ideal case. So, you are asking what is the mean square end-to-end distance in a given solvent compared to the mean square end-to-end distance. So, this is mean square end-to-end distance. And that is quantified by the expansion factor called alpha, which is simply a ratio of mean square end-to-end distance in a given solvent to that in the equivalent theta solvent. Now, one thing to keep in mind here is if alpha is greater than 1, solvent is considered good, meaning compared to the ideal chain, you have an expanded chain leading to alpha being greater than 1, and obviously less than 1 is going to be a poor solvent. Now, you can see why it is called the expansion factor. There is one more point to be noted here, which is the temperature at which the theta condition is obtained or observed is called the theta temperature, at which the expansion factor is 1. This is also called sometimes the unperturbed dimension. So, this is something you will see in textbooks called unperturbed chain dimensions. It simply means we are talking about ideal chain dimensions, unperturbed by the what is happening around. And what you can see very quickly is that the same solvent can change its quality depending on the temperature. So it can become poor if you go below the theta temperature. Now, so you see how temperature effects are coupled with solvent quality. And the theta condition is very important for understanding intrinsic chain characteristics such as molar mass, etc. And it's one of those unique conditions under which ideal chain conditions can truly be realized in practice. And I would like you to also recall another related concept we have seen in lecture 8, where when we were looking at membrane osmometry, we saw that that was a way to determine molar mass, and we saw that the idea of a second Burial coefficient, and at that point I would have said that that has something to do with the nature of polymer solvent interactions. So at the theta temperature, or in the theta solvent at the theta temperature, the second Burial coefficient becomes 0, which you can obtain from the slope of the graph between osmotic pressure over concentration versus concentration. It's actually expansion. If you stop at the second Burial coefficient, if you stop the expansion at the second Burial coefficient, you can get it from the slope of the pi over c versus c. If you want to recollect some of these ideas, please go back and revisit lecture 8 when we have looked at this idea of solvent quality. Again, you see there's another way now you can think about solvent quality, where at the theta condition, at the theta temperature, in a theta solvent, the second Burial coefficient goes to 0. Now, when you really want to think about dissolution, you are looking at real chains and extruded volume effects, right? And again, we have seen these in much more detail in lecture 9. So, I am just summarizing some of those key ideas from lecture 9. For details, I would encourage you to look at the idea of chain size and scaling from lecture 9. So, just to recap, the freely jointed model for ideal chains involves n rigid links, each with length L, and the orientation of one link doesn't affect the next link. So, the root mean square end-to-end distance scales as n to the half. Now, this is something we have seen. Again, remember that the freely jointed chain does not account for realistic considerations, and real chains have higher end-to-end distance in a good solvent. And obviously, chain conformations are solvent dependent. Only in a good solvent you will get the expanded chain. So, when you have real chains, you have this idea of excluded volume, which is not accounted for in the ideal chains case. It's simply the one way to think about excluded volume is the space around a segment or a region that other parts of the chain cannot occupy. And more formally, it is the effective volume occupied by the polymer, which accounts for both monomer solvent and monomer-monomer interactions. So, when you have polymers in solution, you end up getting these three scenarios as we saw on the previous slide, where the scalings change, going from 0.6 for an expanded real chain in a good solvent to 0.5 for an ideal chain or a theta solvent at the theta temperature, or 0.33 for a collapsed chain in a poor solvent. And so, shown here is a cartoon representation of such a system, where you see that the overall chain size changes depending on the solvent quality. Now, moving further, we now consider the case where we take a solvent, a good solvent, where the polymer is soluble, and we keep changing the polymer volume fraction, and we ask what happens to the solution. You can now talk about at least 3 different regimes. Again, this is a grossly oversimplified picture of what really happens, but this will give us a good physical understanding of the process itself. So, you can consider first the dilute regime, where the chains are spaced apart. So, the polymer volume fraction is quite small enough that the individual chains that are fully solvated are quite spaced apart. And the interaction of each chain is primarily with all the solvent molecules surrounding it. And chain chain interactions are absent. This kind of a condition where chains are in the dilute state or the polymer solution is in the dilute condition, where chains don't interact with each other but interacts primarily with the solvent. This kind of a system is very important for measurements such as radius of gyration, hydrodynamic radius, molar mass, many of which we have seen in earlier lectures. Because single chain properties in conformations become important and you are largely looking at effects of chains without getting effects from chain chain interactions. Now you keep increasing the polymer volume fraction in solution, you will end up with something called a semi-dilute unentangled regime, where now the chains are close enough that they start to feel each other. So one chain, although it's not interacting with another chain, they start to overlap with each other. They are not entangled, but they start to overlap. This overlap can be quantified based on what we call a overlap concentration given by C star, where the chains again, like I said, start to feel the presence of each other and they start overlapping. Now, one way to define the dilute regime is to think about the concentration or the volume fraction being less than the overlap concentration C star. And when the concentration is close to C star, you get the semi-dilute unentangled regime. At which point, viscosity of the solution, which is the bulk property you can measure, shows a change at C star and beyond. From there, if you keep increasing the polymer volume fraction even more, you go to the semi-dilute entangled regime, where now the polymer has no choice but to entangle. Because it's a good solvent, remember, so it wants to minimize polymer-polymer interactions and wants to enhance polymer-solvent interactions. But now, at concentrations above entanglement, where you're looking at semi-dilute entangled regime, you have a situation where the polymer can no longer afford to interact only with the solvent. It has to start interacting with other chains as well. And one way for it to do that is to entangle. And that can be, that cutoff between the semi-dilute unentangled and semi-dilute entangled can be thought of as an entanglement concentration. And the viscosity shows a significantly higher change once that point is reached and beyond. So shown here is a sample log-log plot of specific viscosity versus concentration, where you see that as you keep going from left to right, you are increasing the polymer volume fraction or concentration in solution, and you come across 2 points where below the C star, we are talking about dilute. Between C star and CE, you are talking about semi-dilute unentangled, and above CE, you are talking about semi-dilute entangled. And you see a change in the specific viscosity to different extents as you go through those transitions. Now, this plot, such a plot is shown for an example polymer, but there are two important ideas that you want to take away from this plot. The first thing is it's a log-log plot, so that you will see many such plots in polymer physics where many of them are plotted on a log-log scale. The second important idea is this becomes very important for polymer processing. Solution properties are largely important primarily for processing, and particularly with reference to biomaterials, there is a very important technique called electrospinning, which we will have a chance to look at in some detail in a later lecture, where you have to operate above the critical entanglement concentration, well above the critical entanglement concentration, for you to be able to form fibers. It's a technique to make non-woven fibers or fibrous meshes which are biomimetic in nature. And there we will see that if you are below in this regime, you will end up forming, you will end up spraying, or you will end up with a phenomenon called electrospraying and not really electrospinning, where you will generate particles and not fibers. If you have to generate fibers, then you have to be well above this concentration. So you see, while this might seem like a idea that we are learning for its own sake, it has very deep implications for how polymer solutions can get processed. And as always, before we conclude, we are looking at bulk manifestations. That's always been the theme in the course. When we take a concept looking at even single chains, ultimately we are asking what is the effect on bulk. So again, as opposed to small molecules where you take a salt and dissolve it, you will not see appreciable changes in viscosity. But remember, polymers are much bigger than solvent molecules. So polymer addition will progressively increase intermolecular friction, manifesting as viscosity changes at the bulk. And oftentimes, you will see many different types of viscosity mentioned, two of which I am showing here. One is specific viscosity, which we saw on the previous slide. It's simply the viscosity of, so eta here is the viscosity of the solution, eta naught is the viscosity of the solvent. So one way to physically think about specific viscosity is to ask, what is the contribution of the polymer towards the solution viscosity over and above that of the solvent viscosity? Another very important idea here is intrinsic viscosity, which is specific viscosity over C, which is also sometimes called reduced viscosity, at infinite dilution. So, in specific viscosity, we asked what is the contribution of the polymer to the overall solution viscosity over and above solvent viscosity. Intrinsic viscosity is an extension of that idea where at very small polymer concentrations, essentially infinite dilution, what is the change in viscosity of the solution? What is the contribution towards solution viscosity? And we are primarily interested in this property or intrinsic viscosity because infinite dilution simply means, from a physical perspective, that the polymer volume fraction or concentration is so small that largely you can think about them as the chains as being so far away from each other that you can now access properties that are important for single chains. And that becomes a very important idea. Hydrodynamic radius, for example, is measured at very dilute concentrations. One of the reasons is so that you can get effects that are largely intrinsically dependent on the chain properties. And as a rule of thumb, for good linear polymers and good solvents, C star is scales as 1 over intrinsic viscosity. Now, intrinsic viscosity is not new to us. Now would be a good time to pause and recall the Mark-Houwink equation that we saw or briefly alluded to in lecture 8, where we've seen that intrinsic viscosity is related to polymer-solvent interactions, molar mass, and chain conformation at infinite dilution. And it becomes important for us, as we saw in lecture 8, because it appears directly in Mark-Houwink equation for us to determine viscosity average molecular weight or viscosity average molar mass. Now, where the solvent quality comes into the picture is this exponent here, which is the Mark-Houwink exponent, where base, it usually is a range typically between 0.5 and 0.8, and the extremes have something to do with the solvent quality. So, it's typically 0.8 or close to 0.8 for a good solvent and 0.5 for a theta solvent. So, you see, we have already looked at 3 different ways to understand solvent quality. We have looked at the second virial coefficient, which is 0 at theta condition. We are now looking at the Mark-Houwink exponent, which is 0.5 for a theta condition, and we have also looked at the expansion factor alpha, which is 1 for the theta condition, because it's simply the mean square distance in the solvent to mean square distance in the theta solvent. When the solvent happens to be the theta solvent, you get 1 for this. So, this would be a good thing for you to keep in mind and remember as ways to understand solvent quality. When you think about polymer solvent systems and polymer solutions, and you are thinking about viscosity manifestations, the Mark-Houwink equation naturally comes to mind, and shown here are examples of or two plots that one is tells you just how to understand specific viscosity over C versus C if you are plotting what really is intrinsic viscosity, as we have shown here. It's at infinite dilution. The other one taken from the Mark-Houwink equation, where the slope here gives you the exponent, which tells you something about the solvent quality. And we're showing some examples of exponent for different solvents and different polymers. Note that temperature has to be mentioned. So, when you look up a handbook, and it's very common for you to look up these data sets from a handbook, you will note that whether it's reported in a handbook or a paper, all of these properties are also temperature dependent. So, the temperature has to be mentioned. So, it's just to give you a sense of what kind of numbers we're dealing with, and I'll just point you to these two where the polymer is the same, but the tacticity has changed. Solvent is also the same, and you see for the same polymer solvent combination, depending on the polymer tacticity, you end up getting different exponents. So, that's a good idea for you to pause and reflect where on this idea where you're seeing that the parameters for the same polymer but different tacticity are different, and that should not come as a surprise to you based on everything that we have discussed in this lecture. With that, we will close this lecture.